I'm not going to use the microphone, so if anyone has any problem in hearing, let me know. Usually people say that I talk loud enough so that there's no problem in that. I appreciate very much the opportunity to come and talk a little science. It's always exciting when you have an audience that's interested in science outside of just their business-related area. So this is an exciting opportunity, and I appreciate Quantum for inviting me over for the day also. We had some interesting discussions today. I'm going to talk to you tonight about a technique which I've been working on really since about 1977 at Monsanto. The technique is called temporal analysis of products, or TAP. And I'll discuss the technique, but I also want to talk some chemistry, and that is a very simple but important reaction. That is the selective oxidation of ethylene over silver. So let me start with a little advertisement, not for really for catalysis. I pulled out this slide. This is I just want to point out this statement at the very top of the slide. This came from the Pimentel report on opportunities in chemistry, and this has struck me in my discussions with upper management, is that 20% of the U.S. gross national product is generated through the use of catalytic processes. So anytime you're talking about catalysis, you're talking about something that's very important to the physical well-being of our nation. It's an integral part of our society. I'm going to be talking about a particular reaction, of course, and that is the production of ethylene oxide from ethylene. And you can see by the size, by the amount of ethylene oxide produced every year, that this is economically a very important product. So the impetus to do research in this area is very clear. There's a fundamental interest in this process because it's very unique, but there's also a very important economic interest. Now, before I go on, I want to make sure that I acknowledge some other people that were important in this work. Bob Maddox is a professor at Stanford University, and Alan Salt was a postdoc who came to Monsanto and originally started this work. Jerry Ebner is a colleague of mine when I was at Monsanto, and we still continue to collaborate. Now, because this is an important process, and because has very fundamental interest, there have been a lot of studies that have been done on the selective oxidation of ethylene to ethylene oxide, and I've listed a few of the studies, and there's still aspects of this reaction that are controversial, or there are still questions that need to be asked. When we looked at this reaction, the possibility of studying it using TAP, one of the things that we were interested in was trying to identify the oxygen. What kind of oxygen is selective in this reaction? And there have been reports, or people have suggested, that the selective oxygen is O2. And this is important because if O2 is a selective oxygen, then it suggests that there is a maximum selectivity that you can have in the reaction. This initial oxygen atom produces ethylene oxide selectively. The oxygen which is left then produces COX. So consequently, it limits the selectivity. There have also been proposals that it's not chemisorbed O2, but it's dissociatively chemisorbed O atoms. There has also been proposed that there is another kind of oxygen that participates in the reaction called subsurface oxygen, and that hasn't been well characterized at all. So one of the things we were interested in, can you use the TAP technique, which is a transient reactor system, can you use that to kind of distinguish these various types of oxygen? And that's what we set out to do. Well, I need to tell you about the Tap Reactor System before we go on and talk about the chemistry. And so let me spend a little bit of time doing that. And I'm going to switch from the transparencies to the projector. Get some power here. Conceptually, the Tap Reactor System is very simple. And for those of you at Quantum who I just went through this, you can now put the machine into coast, and you can remember all about this. It's conceptually very simple. It consists of a small microreactor which holds your catalyst. It consists of a series of valves which allow you to either let a continuous flow of gas pass through the microreactor or else pulse reactants into the microreactor. This assembly is embedded in an ultra-high vacuum system, which consists of 3 differentially pumped vacuum chambers. Inside the third vacuum chamber is a quadrupole mass spectrometer. So in essence, what we do is we either send a continuous flow of gas or a pulse of gas through the reactor and then detect the products coming out the other side with the quadrupole. Conceptually, very simple experiment. The reactor is being continuously pumped on by the vacuum chamber, so in between pulses, for example, the pressure inside the reactor is very low, and it's more or less in equilibrium with the vacuum system. Even though it's conceptually very simple, it's still very difficult to do in terms of actually carrying out the experiment. There are a lot of different kinds of things that you need to think about. And one of the problems is we do this experiment very fast. The pulses of gas that we send in the reactor are very short. In order to collect data in the time scales that we do, you have to have some fairly sophisticated data collection equipment. By the way, as I'm talking, if there are any questions, please interrupt me and with a raise of a hand and ask me a question if I'm not clear on any particular point. This is where the reactor module goes. This is the actual catalytic reactor, which we put the catalyst. You can see there, we just use catalyst particles, solid particles, very similar to the kind of bulk catalyst that you might find in a plant reactor, except perhaps ground up into smaller particles. The reactor itself is about 1/4 inch in diameter and about 3/4 inch long. So this module will fit in your hand. You can take it out of the vacuum system, take a catalyst out of it, load the catalyst back in, put it back in the reactor chamber. Turnaround time is about 15 minutes. I can do a set of experiments with one catalyst, pull out the reactor, put a new catalyst in, and be running new experiments in about 15 minutes. This is the vacuum system. This module fits on this plate here. These are the 2 high-speed valves. And behind it, directly behind it, there's a continuous valve. The whole thing plugs into a small manifold right here. Let me make one other point about the assembly, which gives it the fast turnaround time, and that is the vacuum system that holds the reactor is closed off from the analytical system, which holds the quadrupole mass spectrometer, so that you can open up the system and keep your mass spectrometer under ultra-high vacuum while you vent the rest of the system to your reactor. The reactor itself is very simple. This is a schematic of it. The front of the reactor, we normally put the catalyst particles. In the back of the reactor, we normally pack glass beads to help disperse the gas before it gets to the catalyst particles and also preheat it. There are 2 thermocouples within the catalyst bed, one in the catalyst sample, one in the glass beads. And although we have not done this kind of experiment, one could theoretically do some kind of differential thermal analysis using the technique. The reactor is heated by a resistance heater, and air or nitrogen flows around it to maintain a uniform temperature. The simplest experiment one can do is to simply pass a stream of gas through the reactor and then measure the products that are coming out through the other side. We call that a scan experiment, and that reminds me, I want to pull out. I don't think I got the right slides here. So the first kind of experiment we can do is we can allow gas to continuously pass through the reactor system. In that case, if we had no reaction at all, what we would measure at the quadrupole mass spectrometer would be a mass spectrum. And this, for example, is the fragmentation pattern of butadiene passing through a packed bed packed with glass beads. This would be the same spectrum, or this would be a spectrum of butadiene passing through the reactor system, in this case through a catalyst and partially being converted to furan. So here's the furan peak. Now, although the continuous experiment is the simplest experiment, it's not the one in which we rely on most. The one we're most interested in is a transient experiment. That is where we pulse reactants into the bed and then look at the molecules coming out in a transient fashion. In that case, because the experiments are done so fast, we can't look at the entire mass spectrum. What we have to look at is only a single peak. And then we measure the time dependence of that peak, which represents a particular product in time. So pulsed experiments look like this. This is a single pulse experiment where we're looking at the profile of a pulse, a single gas pulse in time, or single product in time. And notice the time scale here. The time of other conventional pulse experiments, this is very fast. And oftentimes the pulse widths are several orders, two or three orders of magnitude faster than other kinds of pulse experiments. In addition to this, to looking at the single pulse, one can also look at a series of pulses, a pulse train. So one can observe the decay in a series of pulses. If you've got a catalyst that's changing, that, for example, it has an oxide on the surface, and you begin pulsing in a reactant, that reactant reacts with the oxide. If you titrate the oxygen off the surface of that catalyst, then you expect there to be a decay in the amount of product peak because the oxygen is going away. And this experiment allows you to titrate the surface species off the surface. The most elegant experiment that we can do is what we call a double pulse or a pump probe experiment. In that case, we use two high-speed valves. One of the most difficult problems in catalysis is trying to ferret out what's on the surface, what kind of chemisorb species are actually there. And they're very hard, oftentimes, because their life is so short and because their concentration on the surface is so small, they're very hard to observe, say, spectroscopically. There is an interesting trick one can play with the Tap experiment. If I deposit or inject a species that reacts with the surface of the catalyst and forms a chemisorbed species which is not desorbed, if I then pulse another reactant through at a short period of time later, I can trap that species and pull it off the surface, if you will, and actually detect it. So one has a way then of looking at species with a fairly short lifetime that do not desorb from the surface. We call this a pump probe experiment. The initial pulse pumps the surface up with the species that we want to observe, and the probe pulse then allows us to detect that species or investigate it, interrogate it. This represents a three-dimensional plot of the data that would come out of a pump probe experiment. These would be the initial pulses. These dotted lines would be the initial gas pulses that go into the reactor prior to their, coming out of the valve before the reactor is in place. And they're very short. They're very narrow. So in this case, we're pulsing the first pulse. We're pulsing deuterated ethylene into the reactor, and that's this pump pulse. This is what the deuterated ethylene looks like after it's passed through the reactor. It's now shifted in time and broadened because of the interactions with the catalyst inside the reactor. Then at some time later, we send in a second pulse. In this case, it's O2. Here's the initial pulse before it enters the reactor, and here's what it looks like after the oxygen has passed through the reactor. A little bit of the reactants are converted to products, and here are the product pulses. This is the deuterated ethylene oxide that's coming out of the reactor, and this would be CO2. Notice that deuterated ethylene oxide appears when the deuterated ethylene goes in, but doesn't appear when the oxygen goes in. That gives us valuable information about some of the reactions that are taking place on the surface, and we'll talk about that as we go along. Okay, so let me remind you of these terms so you keep these in mind with regard to the various experiments that I've suggested that we can do. And then we'll start talking about some chemistry. I think I'm finished with this now. So we talked about a number of different kinds of experiments that we can carry out in this little microreactor. We can carry out a scan experiment. That's a continuous feed experiment. We just allow a gas to flow through the reactor in a typical kind of continuous fashion that you might do in any kind of conventional reactor system. And then in that case, we monitor the mass spectrum. We can also do pulse experiments, and these are all transient experiments. We talk about a single pulse experiment. This is one using only one valve. And we can send a gas pulse or we can send a gas mixture or single gas into the reactor system. In this case, we're monitoring the pulse shape of the single pulse. We can either do one pulse or we can signal average a series of pulses together. And we typically do the latter. We typically signal average a series of pulses together. We can also do a multi-pulse. In that case, we we might be using one valve, but what we monitor instead of the single pulse is a pulse train, and watch the decay perhaps in that pulse train, or see how that pulse train changes in time. It's particularly useful in doing titration type experiments. And finally, we can do the pump probe experiment. This is where we alternate two valves, and then we monitor the shapes of both valve pulses. Now, one of the key and important features of this pump probe experiment is that we can change the time interval between the two pulses. And that's very important, and we'll talk about that. And that's called the pump probe interval. So that's the time between when we pulse in, for example, oxygen and deuterated ethylene. All right. Now, our interest was trying to ferret out the kinds of oxygen. But the first thing we wanted to do was establish that you could do a reaction, an epoxidation reaction in a tap reactor. Now, I apologize. I was looking at this slide in the bar just a few minutes ago, and realized that my computer had made a mistake. It substituted H everywhere that I had punched in D. So this work is all done with deuterated ethylene, not with normal ethylene, and I apologize for that. So this would be the product peaks what the product peaks would look like in a pulsed experiment in which we've looked at a specific mass intensity. So mass 48 then represents deuterated ethylene oxide, and that's this peak A. Peak B is mass 46, which would be a fragment peak with losing one deuterium of ethylene oxide. That's peak B. Peak A and peak B show you the relative intensity of the two. They have the same time profile. If you were to normalize the peaks to the same height, they would have exactly the same profile in time. Peak C represents mass 44, which is CO2. Notice that we have shifts in time, indicating that one product takes longer to get out of the reactant than the other. And that's an important feature of the TAP experiment, is that we can measure the relative amount of time that reactants and products stay inside the reactor system. So let's continue on. We certainly can see products. We can see epoxidation and also complete oxidation products in the system. Well, I'm going to show you that next. So we run this as a series of temperatures, and they're listed. And what you see if you run this as a series of temperatures, you get a change in conversion depending on the amount of temperature, as one might expect. And you can, in this sense, one can use the TAP system as a highly differential reactor. Conversion in the system is around 1%. Molecules move through very rapidly, and one can calculate then that from this in this differential mode, can calculate an activation energy. So you can see that what I've done is I've plotted the various peaks as a function of temperature. Notice also the time resolution here. These peaks are coming out 4.4 milliseconds after they were initially injected. So the experiment is very fast in terms of the time scale. And if you make an Arrhenius plot for ethylene oxide production, it turns out, and you calculate an activation energy, it turns out to be about 4.5 kcals, which is consistent with other people's measurements of the activation energy on the system. All right, we looked at the oxygen. Let's look at this. Let's look at the temperature dependence of the CO2. Now, notice something very interesting has happened. Is that the temperature dependence, the amount of product formed is drops, but the peak shapes dramatically change, and that's indicative of either a very slow reaction or some type of adsorption-desorption phenomena that's taking place on the surface of the catalyst. So it was unexpected to us when we were running the experiment. We hadn't done a very careful literature survey prior to that, and we didn't know that other people had noticed that you could form some type of chemisorb CO species on the surface. So what we wondered at this time was this change in the shape of this product, was it due to the fact that CO2 was chemisorbing on the surface, or was it due to the fact that this reaction was very slow? How do you test that kind of issue? What you do is you pulse CO2 as a reactant through the reactor and see whether it's strongly chemisorbed on the surface also. If it's not, then you can, from this, gather that this has to do with the reaction. So we made a comparison. In this case, peak A is CO2 added to the reactor as a reactant, not formed as a product, and peak B is the product formed. You can see that there is some difference in time, but they're essentially identical, indicating that what we're looking at is the adsorption, desorption qualities of the CO2. So CO2 becomes strongly adsorbed on the surface of the silver. All right, so now we've kind of learned a little bit about the products and the reaction, the fact that we're getting data that's very consistent with what people are seeing in the literature in many respects. And we decided we needed now to probe the reaction itself and try to understand the relationship of, or whether we had O2 or chemisorbed O atoms. Well, how did we think we would do that? The concept of the experiment is very simple. We thought we'd do a pump probe experiment. First pulse, and this shows the pulse before it goes into the reactor system. I didn't point out that these initial gas pulses that we're injecting the reactor system, the pulses, the gases that are coming out of the valve, the pulses are about 200 microseconds in width. So they're very, very narrow, the initial gas pulses. And this is what the initial gas pulse looks like. So we decided we'd pulse in oxygen at time equals 0, and then about a quarter of a second later we'd pulse in deuterated ethylene, and we'd look at the ethylene oxide production. We reasoned that if O2 were the active species, that because the O2 exits the reactor in a short period of time after it's injected, that if we move these pulses closer together, and since O2 has a short lifetime, that as we got them closer together, we should see more conversion or more ethylene oxide produced if O2 were the active species. So our idea was to change this pump probe interval, and then what we imagined we would see would be an increase in the amount of ethylene oxide produced if the O2, if a chemisorbed O2 species were the active species. Now there's another important point about this, is you notice we're pulsing in oxygen and we're pulsing in deuterated ethylene. This isn't just a single pulse experiment. This isn't a one-shot experiment. We're actually sending in a series of pulses. We send in an oxygen pulse, a deuterated ethylene pulse, then we send in another oxygen pulse. So we're sending in actually a pulse train, and we're signal averaging everything together. The important point that I want to make about this is that the only place that we see ethylene oxide formed is when ethylene goes into the reactor. That indicates to us that there's no chemisorbed ethylene that stays on the surface, then is subsequently converted to ethylene oxide. And that's another important point. So now we know that the reaction occurs directly between ethylene oxide and some kind of chemisorbed oxygen species rather than some activated form of ethylene oxide and oxygen that comes and interacts. So now let's do our experiment. Let's take the pump probe interval, let's change it, let's shorten it, and let's watch and see if the ethylene oxide increases. Wait a second, that doesn't look right. Look at the change. It didn't increase, it decreased. Now when I saw that, I said, hey, something's wrong with this experiment. That doesn't make any sense. I don't understand that at all. So I began to suspect that perhaps somehow the way in which we were pulsing gases in was somehow influencing the amount of product that we're seeing. It was extremely disturbing to me at this time. I thought that the experimental aspect was something was wrong with the experiment itself. That somehow, because we had moved these pulses close together, that the amount of product was being influenced by the closeness together. I didn't understand exactly what was going on. it just didn't make any sense to see a decrease in the amount of ethylene oxide we were producing. So we did another experiment, and that is, instead of using, we did a pump probe experiment, but we used inert gas to see if the inert gas changed in intensity at the various levels that we're looking at, to see if it changed in intensity as I changed the pump probe interval. So now we pulsed in krypton and looked at the krypton intensity as a function of its position. It didn't change at all. Nothing was wrong with the experiment. Something was happening that we didn't understand, but it was fascinating to us. So we began to change the pump probe interval by a fair amount. And what we found is that this was a real phenomenon, is that there was a maximum in your ethylene oxide yield at some point, and as you got closer and closer to the oxygen pulse, here we're changing. Here's the oxygen always comes in at time equals 0. Here ethylene comes in at 4.5. Here, as you see, we're changing the time. As you got closer to the oxygen pulse, you decreased the amount of ethylene oxide produced. Maybe there's an activation process that's taking place on the surface of the catalyst. Maybe that's what's causing this. It takes time to activate the oxygen, and as a result of that, you don't see the maximum yield until after a period of time. And that's been proposed, that there's a certain activation process that has to take place. And maybe that's what we're looking at. However, it seems like that's an awfully long time for a real kind of chemical activation. Maybe there's some kind of reorganization of the surface, and that's what's taking place, and that takes a period of time. So how do we test that? Well, let me digress from this a minute and look at some other data. And this is from a tap pump probe experiment. Now we're going to measure the relative CO2 and deuterated ethylene yield as a function of the O2 deuterated ethylene feed ratio. What we find is that as we decrease the oxygen relative to the ethylene, the amount of deuterated ethylene formed goes down. So the amount of oxygen on the surface is influencing the selectivity of the reaction. The higher the oxygen to ethylene ratio is, the higher, the more ethylene relative to CO2 formed. So there's something important in terms of, it's not only active oxygen, but you have to have the surface already covered with a certain amount of active oxygen to get selective oxygen. Okay, so that's another clue. Okay. So what did we find? Well, it's still a mystery today exactly what causes that, but we think we know. And I'm going to have to do a little drawing here to explain this. If you look at the data and look at the CO2 produced in this reaction, and you plot that up on our time scale of our pump probe experiment, we pulse in oxygen at time equals 0, and then we pulse our deuterated ethylene at some time later here. This is the interval. So this is the pump probe interval. You look at, it turns out that you recall I showed on the very first slide of the pump probe experiment, I indicated that CO2 was produced when you pulse oxygen in. Turns out that there's carbon left on the surface of the catalyst. Remember how strong the CO2 chemisorbs to the surface of the catalyst. What we find is if we draw a profile of the pulse of CO2 that's coming out of the reactor, that it looks like this in time. It's very broad. So what we have is we have some kind of carbonate on the surface of the catalyst, and that takes a period of time to exit the reactor. Turns out that our maximum and our peak of ethylene oxide production is down in this area, when the maximum amount of CO2 is out of the reactor. The minimum is in this area when we have the maximum amount of CO2 and what we think is carbonate adsorbed on the surface. So in effect, what's happening, what we imagine is happening, is that there is chemisorbed active oxygen on the surface, but it's bound to, it's formed a a carbonate type species, and it's blocking those sites. When you reoxidize the surface, when you add more oxygen, you allow that carbonate species to leave the reactor system, open up the active sites, which then can react with the ethylene oxide. This also might say something about how the oxygen gets into the catalyst, but we're not sure about that yet. So we think right now that the reason that we're seeing that reduction is that CO2 are blocking sites. And I think there is also evidence in the literature that CO2 affects the reactivity of the system and perhaps the selectivity of the system. That's something that we're interested in and we're pursuing right now. Now let's see what we've learned. First of all, from our pump probe experiments, since we can do the pump probe experiments and we can inject oxygen in and then look at it at some time later, and we know that the half-life of O2 from other measurements indicates that the half-life of O2 is very short relative to the half-life of O, it's pretty strong evidence that O2 is not the active species, but that you actually have to have chemisorbed, dissociatively chemisorbed oxygen atoms are your active species. The fact that we can move these pulses closer together is also strongly indicative of the fact that it's not O2 that's reacting. When we have the greatest amount of O2 in the reactor system is at time equals 0, and that's when the lowest amount of reaction is taking place. So it seems pretty clear from these studies that O2 can't be the key player in this reaction. The other thing we were interested in was the and here's let me put this one other piece of data up with regard to the length of time that the active species is on the surface. In this case, what we did was we did a series of experiments where we had no oxygen. We had oxidized the catalyst initially, but then we turned the oxygen off. So we pulsed only deuterated ethylene over the catalyst, and we in effect titrated then the amount of active oxygen that was left. And what we found is that we started out with a relative value of 10, and that dropped off fairly dramatically in a series of pulses. So there was active oxygen which stayed on the catalyst for a long period of time. This is, in this case, we've waited 5 minutes since we've oxidized the catalyst. So there's active oxygen on the catalyst after it's set under vacuum for 5 minutes. That's a clear indication that we're not using O2. This is still active and it drops off very quickly. There's also a change in the selectivity as this drops off. So finally, let me show you we were also interested in what we called subsurface oxygen, and that is there oxygen underneath the catalyst, this active oxygen that's in the that's actually selected. So what we did was we did a series of experiments where we initially oxidized the catalyst at high temperature, that's greater than 400 degrees C. We oxidized it at high temperature with oxygen 18. And then we pulsed into the reactor a mixture of ethylene and oxygen 16. And what we found is that after a series of pulses, we detected ethylene oxide. We detected some of the oxygen 18 in the ethylene oxide, indicating that the O16 was interacting with the subsurface type oxygen species. Subsurface oxygen is stable up to 400 degrees. Any kind of chemisorbed oxygen will decompose well below that temperature. This is an important finding because it's been theorized that the subsurface oxygen is responsible for non-selective oxidation, where the chemisorbed oxygen is responsible for selective oxidation. We think what this shows is we haven't been able to distinguish between the two, but we think that what this indicates is there is an exchange between the subsurface oxygen and also the surface chemisorbed oxygen. So let me summarize some of the things that we think we found now and we understand about this reaction. Conclusion. First of all, we believe that we've clearly shown that adsorbed atomic oxygen is responsible for oxidation. And that's an important question that's been asked for a long time. And we think that there's very clear evidence now that certainly is the case. Secondly, we think that the rate, which is also shown by other studies, that the rate of oxidation depends on the concentration of this chemisorbed oxygen and involves a direct reaction of ethylene with this species. There's another point here is that that you have to have that the fact that the rate of not only the rate but also the selectivity of this reaction depends on the amount of chemisorbed oxygen. Also depends on the amount of chemisorbed oxygen on the surface. So the nature of the oxygen changes as the surface coverage changes. We also found that subsurface oxygen is incorporated into both CO2 and ethylene oxide. We can't distinguish right at the moment whether the subsurface oxygen is only involved in the non-selective reaction, but we do know that there is an exchange between the subsurface and the chemisorbed oxygen. And finally, we found that CO2 is strongly adsorbed at reaction temperatures and may affect the catalytic activity by reacting with the chemisorbed active oxygen. And we think this has important implications in how you run the reaction. And we're going to study how it affects actually the selectivity as well as the activity in later experiments. Thank you for your attention. If there are any questions, I'd be happy to answer them.
What is the evidence that you have subsurface oxygen?
Well, if you take the catalyst,
First of all, how do you define it? How many layers down?
well, that's why we call it subsurface oxygen, because it's not clear where it is, and it only has recently been. That's not our name. That's a common name in the literature, but it's only recently been evidence that it exists. What you do is you do the following. You know that chemisorbed oxygen has a very short lifetime on the surface at certain temperatures, and that silver oxide decomposes at certain temperatures. So what we do is we first of all, we start off with our catalyst, and we chemisorb O2 on the surface, and we heat it up. At a certain temperature, the O2 has a very short half-life. In fact, let's say about, I'll try to pull this out of my head. This may be wrong, so this is not. Let's just say that at reaction temperatures, the half-life of O2 is about 10 to the minus 4 seconds. Okay, so at 200 degrees C, half-life of molecular oxygen is too short. So it doesn't stay in the reactor any length of time at all. The half-life of O chemisorbed O atoms is longer. But if I heat the reactor up, if I take it from 200 up to 400 degrees C, that should recombine and come off as molecular oxygen. But I can then test the surface to see if it's reactive. And if there's any chemisorbed oxygen on the surface, it should still react. And you get no reaction after you go through this process. You don't pulse any more oxygen, you get no more reaction. If you started off then with O18, and you've gone through this process, then we can assume that there's no O18 on the surface as chemisorbed O18. However, if we then run reactions with O16, and we pulse O16, and all of a sudden O18 appears, then it must be underneath the surface somewhere. It must be subsurface. So that's the basis of that conclusion, that exists on the catalyst. Now there's another important aspect of this, which I haven't discussed because we don't understand this yet either, is that we found that there's an actual activation process in making this catalyst work. And if you have just clean surface, just clean silver, that you don't have anything, you haven't pulsed oxygen over it at all, it's not active to oxidation. You have to go through some type of activation process, which we think, and there are other speculations in the literature which indicate this is true, that you have to create this subsurface oxygen species. It's thought that the active catalyst actually looks like this. where this represents the subsurface oxygen, and then the chemisorphed oxygen is a O-atom on that surface. Yes.
Can you address the role of promoters on this reaction?
I'll address the role of chlorine because I have a feeling. As for cesium, I don't. We have not done any work with promoters, but the current ideas about that is that you replace the subsurface with a chlorine atom. The subsurface is nucleophilic. Subsurface oxygen is nucleophilic. The chemisorphed oxygen is electrophilic. Chemisorphed oxygen reacts with the C double bond to form ethylene oxide. The subsurface reacts with the hydrogen, pulls off the hydrogen, and you form the alcohol, which then goes on to produce your non-selective products. If you replace this subsurface oxygen with chlorine, it still activates the catalyst, but you no longer can have this kind of non-selective reaction. And I think that's the concept that's involved in it. And you don't have to have very much chlorine, which indicates that it is of a surface property. So that I think that seems pretty reasonable. We're doing work in that area right now. And we're very interested in trying to see how it correlates with the other things that we see. Yes?
I have a difficulty about your explanation for the CO2 absorption on the surface and then releasing with the oxygen when you bring the two pulses together and decrease in the concentration of the formation of ethylene epoxide.
Yes.
If that's the case, that if carbon dioxide is absorbed on the surface in the form of carbonyl or whatever you are suggesting, so this
Addition is positive for endothermic. So what we see then is that we have exothermic chain growth, endothermic chain insertion. This suggests that might explain why the formation of aldehydes and alcohols on the surface of metals such as iron, nickel, and platinum doesn't occur as readily as the formation of hydrocarbons. And that would be because the step that is critical to forming the C2 aldehyde here is endothermic, and therefore unfavorable. Another thing that we can deduce from this slide concerns the formation of hydrocarbons. We'll notice the activation energy for the formation of olefins is higher than for the formation of carbons. And so we would expect that as we increase temperature, we would make more olefin than carbon. This has in fact been observed on hydrogen in our laboratory. We work at very high space velocities to avoid the secondary hydrogenation of olefin, which causes, as you increase the temperature proportion of olefin product increases. So the conclusion here then is that the theory does give us additional insights into the surface chemistry. Well, I've listed here the conclusions I'd like to bring out from this talk. I've shown you that the activation of CO is affected by metal composition and dispersion, interactions with absorbed CO, and interactions with metal oxide species that are present on the surface of the catalyst. We've also seen that chain growth occurs by a mineralization process known as C1, species partially hydrogenated. And we've seen that the terminal olefins that are produced as a primary product can participate in chain initiation and chain propagation. Now, let's take just one more minute here to ask, what does this all imply for the future? Well, what we've seen is that we can manipulate the activity of these catalysts by the introduction of olefins, particularly metal oxides. This, I think, holds a lot of promise for making very active and possibly selective catalysts for the synthesis pre-primitive years till the future. I know that there's a lot of active work both in industry and in academic institutions in this direction. We've now convinced ourselves that the growth of chains, these binding products, is a polymerization process. The only thing we can control here is the degree of polymerization, or the ratio of the propagation various graduate students who have worked with me during the past 15 years in this area. Without their efforts, this work would have been possible. In the middle here, I've identified 3 individuals who have worked with me. These are senior investigators. Michael Duncan is a researcher at AT&T Bell Laboratories, introduced us to MR spectroscopy. James Sisterovich, as I mentioned, is at Kodak Laboratories, still collaborating with them. Mike DePontis was a postdoctoral student who came and worked with us for a year in South Africa. Missing from the slide, rail mission is Katrine Lee, who has recently been working with me. She is from the University of Paris. Finally, I'd like to also acknowledge the support of the U.S. Department of Energy. Mention that without the financial support, none of what I'm saying would be possible. Thank you very much for your time.
Thank you very much. It was really a fascinating lecture. And I'd like to
Turned around from the shell in the middle of